Hi everyone, welcome to the second and last video of this week. And in this part, we will have a tutorial say about the mice package for univariate missingness. Here on the HTML file is not showing up, but I I have added the reference to the manual package of the manual of the mice package that is available in Cran and describes all functions, what the functions take as arguments, and what are the output returned. I know that I have uploaded the paper describing the package to learn, but the paper is from 2011, and although most things remained the same over the years. The package has been changed, modified, improved, and so some details have changed. And we will concentrate in the case of univariate missingness in this part. And I have simulated some data. I know that real data is more interesting, and I promise that next week we will have an example with multivariate missingness with real data. I know that I'm always saying that it's next week or it will be in the near future that we will be analyzing real data, but next week is for sure. It's also the last week, so if it's not next week, it will not happen, but it will happen. Okay, so but without further ado, what I have said is okay, I will generate 100 observations, and I will put myself in the context of my analysis of interest. So how I'm generating data from a linear regression model. I have two covariates, axis 1 and axis 2. Axis 1 follows a univariate, it follows a uniform distribution on the interval 0, 5, and axis 2 also a uniform distribution, but on the interval 0, 10, 0, 10, sorry. And uh, this is the betas that I'm using to construct my response, and my response follows a normal distribution with this mean function. So beta 0 plus beta 1 times x1 plus beta 2 times x2, and the variance is 1. And then I will impose MAR missingness. So I will say that some values in axis 2 are missing when the corresponding axis 1 is above some threshold. In this case, it was 4.2, and for this specific seed it gives me 13 missing values over 13 missing values in out of 100 generated values. And then I constructed a data frame because mice needs data frames. Okay, so I will run just this. And the mice package has a function that returns the complete cases, and this CC function. So I have called the data frame with our simulated data sim data, and in this case it's a context where we have missing in the covariate, say, right? So we have used axis 2 as a covariate, and we have imposed missingness on axis 2. It's simulated data, but just to illustrate, we will just, the purpose of this tutorial is just to illustrate the functionalities and how mice works in practice, okay? So if I run this chunk, so basically what I obtain is the data frame, and here it's the record of the number of the observations in the original data set. So for instance, I know that the fourth value is missing, the same for the sixth and the seventh, and so on and so forth. And this is my the complete cases of my data set. So my data set is y1, x1, x2. I have some missing values in x2, and under complete cases, they have been removed, right? And also, if I do this, what is the number of rows of my complete case of my complete cases data set? I get 87, and it makes sense because I know that I have 13 missing values, right? So all good. And if we remember and if we go back to week 2, where we learned about some visualization tools for missing values, we have looked at this md dot pattern function that basically gives us the patterns of missing data. Here it's pretty simple, right? I know that why is this not showing the entire plot? Well, let's come here. I know that I have 87 values for which y1, axis 1, and axis 2 are observed, and then I have 13 values for which axis 2 is missing, but y and axis 1 are observed. And there is also another function that it's clearly more useful when we have several variables with missing values, that it's this function md dot pairs, and basically it gives us the pairs of variables in our data set for which the variables are observed and missing. So basically, for two variables, we have four possible patterns, right? The two variables are both observed. One of them is observed and the other is missing. The other way around, one is missing and the other observed, and both are missing. And this MD pairs, it's exactly what it does. I know that y1 and axis 1, they are all observed, and axis 2, for instance, I know that there are 87 values for which axis 1 and axis 2 are observed, 87 values for which y and axis 2 are observed. I don't have missing values in y and axis 1, that's why the zeros here. And I know that there are 13 values for which y is observed and axis 2 is missing, 13 values for which axis 2 is observed and axis 2 is mixing, and the other way around, for instance, here is the number of values for which y is missing, because there are no missing values in y. These are all zeros in this row, and the same applies to axis 1. And here I have 13. There are 13 values for each axis 2 is missing and y is observed, and uh, the and the same here, 13 values for which axis 2 is missing and axis 1 is observed, and missing or observed, no. And then missing, I know that there is 13 values for axis 2, axis 2. Okay, so this is most useful when we have many variables and we can look at some pairs and have an idea of what is going on. And okay, let us start now with the mice package. And what we do is to impute the values in axis 2. So let's start with step 1. And I know that axis 2 is a continuous variable, correct? And by default, mice will use predictive min matching with type 1 matching and 5 donors. And also by default, the number of iterations, or not the number of iterations, sorry, the number of copies of the dataset, M capital, what the letter that we have been using to denote the number of copies of dataset, M capital is 5 by default in mice. Okay, and I will use the mice function. What I need to pass is my data frame with the variables, the observed and those with missing values. And if I do not want to change any of the defaults, I do not need to do anything else. I'm fixing the seed because we know that we will be, even in predictive min matching, right? We estimate the regression model based on the observed data, so there is nothing stochastic there. But then we are using d equal to 5, so we have 5 possible donors, and then we select at random one of them. And if we do not fix the seed, every time we run our procedure, we will obtain a different value, right? Because it's at random, so we can by chance obtain the same donor, and or it's kind of difficult that without fixing the seed for all the copies of the dataset, the 5 copies, that we will get the same donors just by chance. But fixing the seed outside, it does not work, because mice inside is using random numbers for different things. Here, it's the only thing, it's to select the donor, the only random step, let's say, that we have. But fixing the seed outside does not work, so we have an argument that it's seed. And we can also type, if we type uh, we see what are the arguments of the function. Here we have the default method. It's predictive min matching for continuous, logistic regression for binary, and the other for the other types of variables. And you can have a more close look in the arguments of this mice function. Okay, what and I've set the argument print flag equal to false. The default is true, and basically it prints on the on the console, on our console, the history of the imputation. And I don't think that it's very interesting, so I'm setting it to false. And okay, I will not change right now any of the defaults. I will save this in an object that I have called imps. Not very creative, but that's it. I will run the chunk, and uh, this is when I call my object. This is the information there I get. The class of the object is MIDS, which stands for multiple imputed data set, and is a special type of object that mice creates for storing the imputed data set. Then we see that the number of multiple imputations, or the number of created data sets, is 5. And then the imputation methods used here, because we don't have any missing values in y and x is 1, we don't have any. And here for x is 2, that has missing values, we know that predictive min matching PMM, in that's the abbreviation in mice for predictive min matching, that's the method that has been used. And here in this predictor matrix, it's telling me which variables are used to impute the others. The default in mice is for every variable that has missing values, I use all the others. Even if the others I have missing values, I will use them too. We have seen this back in week 5 about multivariate missingness, right? We kind of do an initial run and fix the missing values to some random draws of the observed ones or to the mean, and then we use all the variables to impute, and we need to do this in an iterative procedure. Here we will explore this in much more detail next week when we talk about multivariate missingness. Here we only have one variable with missing values, x is 2, but it nonetheless says, okay, in case y had missing values, mice would use x is 1 and x is 2. X is 1, in case it had missing values, mice would use y and x is 2. In this case, x is 2, we know that we have missing values. Mice has used y and x is 1 to impute x is 2, right? So our model is of the form, our imputed values is the regression. Then we do predictive min matching, but the basic regression model to compute the predicted means is that a value in x is 2 is equal to some constant plus some coefficient times x is 1 plus some other coefficient times y. And then we form our predicted means for the observed and for the missing, and we know what mice is doing. Okay, and we can then, and we will see this in a few minutes, if, for instance, we do not want one of the variables, for instance, say that we do not want x is 1 to impute x is 2, so we want just y to contribute to the imputations, we can customize this predictor matrix and tell mice what we want. Right now, we are just looking on what mice does by default. Okay, and we can also then we have our object imps, that where we have saved the results from the step 1 from the mice function. And for instance, I can look at the imputed value. So I have done 5 copies of the data set, m capital is equal to 5. So these are the imputed values. This is the ID in the original dataset. So I know it's the 4th value in my dataset, number 6, number 7, so on and so forth. I know that I have 13 rows because I have 13 missing values. So this is the row or the column, sorry, corresponding to the imputed values for the first data set that we have created, for the second, and so on and so forth, up to the fifth copy of the data set that we have created. And in case I want just to look at the first set of imputed values for the first copy, I can just use what we have done, and I just extract the first column, and this is giving me what it is here, sorry, here in this first column. That's what I have here, and I can do the same for the second and the third. This is useful in case, for instance, that I want to do then everything by myself. I just want to use mice to impute the missing values, or I want to do some exploratory analysis, look at the missing values, so I know how to extract them, the missing values, not the imputed values, sorry. I know how to extract them, and I can do then everything by myself if I want, or I can have a closer look at them. And this is just the imputed values, but it's useful also if I want to do everything by myself, or I want to do some exploratory analysis based or on the complete cases or on the completed data sets after imputing the missing values. If I want to extract the the completed data sets, and this is done through the use of the complete function. If I run it in the file that I have uploaded, it's not showing because then it will print the two data sets with 100 rows, and I don't think that it's very useful in case you want to print the PDF. So I've used results equal to height, but you know how to extract. And here I have, this is the first imputed data set. So I have all observations, the observed portion that we have talked last week, and the imputed values. And here it's the second, and I can do the same up to the fifth data set. Okay. And okay, after having imputed the values, it's not a bad idea to look at them, right? To see. I know that with predictive mean matching, at least I do not incur in the, or I don't risk imputing, for instance, negative values or whatever, but I also want to know if the values that are being imputed somehow resemble the values that I have observed. They don't need to be exactly equal, but their distribution cannot be terribly different from what we have observed, right? Because missing values, it they are values that in case they would have been observed, they would follow, say, the same distribution of the observed values that we have. Not they need to be exactly the same, but if we see something completely different, then this should flag or ring a bell saying something is possibly not going well. Okay, so we have mice as several functionalities. This common, the strip plot, basically what it does is for each of the variables that we have in our data set, the blue circles are the observed values, and the red ones are the imputed. Here, because y1 and x is 1, I will look here, I think they look better here, because y1 and x is 1, they don't have any missing value, so I only have blue values. And here I have the red values, and this is for the first, second, third, fourth, and fifth imputed data sets. Here 0, it's because mice does a setup run, so just ignore this. We are not imputing anything, and we will come to this in a minute, to the setup run that mice does. But here we are looking at them, and okay, the red values, they look good to me. Also, this function that plots these circles, I think it's most useful when we only have a few data points, because when we have too many data points, here we have 87 observed and 13 that we are imputing, it kind of becomes a little more difficult to visualize things. So we can also ask for the box plots of the observed and imputed data. And again, y and x is 1, they don't have any missing values, so I'm only seeing the box plot of the observed values. And here I'm seeing the box plot of the observed values here in the 0, right? And then so here the 0, it's not really the setup run, is the observed values. Okay, 0 because the setup run is for a different thing. Sorry, I've messed up here. The zero is where we are plotting our observed data. Yeah, it's also related to the setup run, but basically we only have the observed data, and then we can compare. For instance, here the box plot. This is the box plot of the observed against the imputed values, and okay, I think everything is going well. Obviously, I've simulated the data, and I've simulated data under the MAR missingness mechanism. It's a linear regression. I know that Y and the axis 2 are very much correlated because axis 2 acts as a covariate in Y. So I know that things need to work well. But to illustrate things at the beginning, I think we want to see how things should work. Then we can take care of the problem of how things with many variables with missing values, sometimes things do not work so well. But okay, without further aside comments here, everything looks fine. There is another option available, and it is to plot the kernel density estimate of the observed data against the kernel density estimate of the imputed data. And if we run, that's what we obtain here. I think it looks better here. So in red are the kernel density estimates of the imputed values, and in blue the kernel density estimate of the observed values. And here we should notice something. We know that it's predictive min matching, right? So with predictive min matching, and I know that my axis2 variable was generated from a uniform 0-10 distribution, but even if it was with real data and I didn't know what was obviously the distribution that was behind, but I could look at the values and they are all positive. So with predictive min matching, it's impossible that I will impute a negative value because I'm using the observed values to impute the missing one. So if the observed values, they are all between 0 and 10, there is no way that I can impute a value below 0 and above 10. But here, if we look at the kernel density estimates, we see that there is some mass, for instance, some positive mass assigned to negative values. And this has two reasons. First, kernel density estimates, they are a non-parametric density estimator, and in the case of the imputed values, we only have 13 values, right? Because we are imputing the missing values and we have 13 of them. So kernel density estimates with 13 observations, they can be dangerous, and sometimes we see these multimodalities and we know that they are really not there. And more than that, kernel density estimate, this use kernel density estimate, the common density that is used in R, that's what mice is using. And by default, it's a normal kernel. And we know that normal kernel, it assigns positive mass to the negatives. And because we have some values that are close to zero, both in the imputed and in the observed, by using a normal kernel, we are assigning positive mass to the negative. So this this is not a problem, so nothing is going wrong with our imputed values. That's what we want to be sure. It's just that when we look at this plot, we should be aware that first we have only 13 observations and kernel density estimate. It's a non-parametric density estimator, so we need, I would say, 20, 13 values to be a little bit more confident in the density estimates that we obtain. But the most problematic point is that we use a normal kernel, and when we have observations close to zero, almost surely we will impute, not impute, we will assign negative, we will assign positive mass to the negative value. So not a problem if we look at the box plot, but I thought I would or I should make this disclaimer or warning. Okay. And that's it in terms of the diagnostics of our imputed value. There are three ways of checking our imputed values. And of course, as Van Buren says in his paper describing the mice package and also in the book, when there are some mismatch between the observed and the imputed values, then there are several possibilities, and it is slightly more difficult to know what is going on because the mismatch between the observed and imputed distributions can be due to the fact that we are using a bad imputation model. So we need to improve. We know that what mice does by default. So basically we need to change our predictor matrix or to see what are the variables that we are including. This is something that we will be discussing next week. Or because the missing mechanism is not missing at random. It can be that it's missing not at random, or because by a combination of both. No, the missing mechanism not being missing at random, and also our imputation model not being a good one. So when we see some mismatch, we need to do some more investigations. Okay. Now let's see what just not see just illustrate if we want to change the defaults. For instance, we know that we are using predictive mean matching, and we know that, or I telling you that predictive mean matching, so we have mice dot impute dot pmem, and this is the arguments of the function that use predictive mean matching to impute the values in our call to the mice function. And we know that we have match type. This is what we have seen in the last video. If we come here, we say that zero distance between predictive values, uh, one, the type one matching, the type two, we have seen the three of them in the video, the number of donors that by default is 5, so we can change the match type and the number of donors, for instance. And I don't need to change nothing here. For instance, I don't need to change or to use the mice.impute.pmm function. I can just, in my general call to the mice function, change the arguments that I want in this function to be changed, and mice behind the scenes say will change everything in this function. Okay, so for instance, say that I do not want to use 5 donors as the default. I want to change it to 3. I come here and I change donors, the argument, to 3. And also here it's not in the mice_impute.pmm, but it's on help mice. M by default is 5. We know if I want to change, I just also, if I want to change the number of copies of the dataset that I'm doing here, I say, okay, I will use 3 donors for predictive mean matching, and I want to do 10 copies of the data set. And that's the arguments that I'm changing. Just putting here on the right side. Okay. Okay, so I do this, and if I run the chain, it's fine. We now see that it's giving us that we are using 10 imputed dataset. The predictor matrix has not changed. We have not changed nothing, and also the method that we are using, we also haven't changed it. And suppose now that we want to change the default method. We do not want to use predictive mean matching. Suppose that I want to use the bootstrap version of the stochastic regression imputation, and I know that it's available under norm.boot, and so there are 2 ways I can change it. I can just come here to the mice call and change the method norm.boot, and here, because I only have one variable with missing values, I know that what I'm doing is I'm changing the imputation method for the variable x is 2. I think in general, if we do this, it will change the method for all continuous variables. If we have, for instance, say x is 1 and x is 2 with missing values, and if we change the method, it will automatically change the imputation method for both x is 1 and x is 2. And if I do this, for instance, and these are the imputed values that I'm generating, and if I do, let me just do something. So that's my object, and now I see that I have changed the method to impute x is 2. But in case I have several variables and I do not want to change, for instance, say that I see that I'm imputing x is 1 and x is 2, and x is 2, it looks pretty normal. So I want to, sorry, x is 1 looks x x is 2 looks normal, and x is 1 does not look normal. So if x is 1, the distribution does not look normal, I want to use predictive mean matching. But if x is 2 looks normal, I want to use one of the methods based on the normal assumption. And and if I have several variables, I can change the method of imputation for several of them. So what I can do is I do a setup run of mice, and by doing a setup run, I just pass the data and I put maximum iterations equal to 0, I will run this chunk, and then, for instance, I've saved this in the object imps 0, and if I call imp 0, uh, that's what I obtain. And then not what I obtain. This is after I've changed. So if I run this, it's PMM, and now I want to change the method. So I'm coming here and to my object imps 0, I'm calling the method part, okay? And I'm saying that the method to impute, I can do this. And now I'm saying that the method to impute axis2 is norm.boot, okay? And after doing this, I see that I have changed the default, okay? And here I'm no longer doing the setup run. What I need to do is I do a setup run, I change the method to what I want. In this case, is the variable axis2 that I want to use norm.boot, and then I do my call to the mice function, and in method, I put met is this object that I have created. I put here the name that I have used to save the what I'm changing in the method of imputation. And this is useful when we have several variables, as I said. And I can also do a similar trick to customize my imputation model. For instance, here, I'm seeing that, where is it? Yes, here I can do exactly the same thing. I did my setup run of mice, okay? And imagine that I want to change my predictor matrix, okay? And my predictor matrix is that matrix formed of zeros and ones. And uh, imagine that I do not want my predictor matrix, or I do not want in axis2, the variable that I'm imputing, I only want to use y. I do not want to use axis1. I know that mice by default uses both y and axis1, but I only want to use y, not axis1. So I come here to my predictor matrix and I'm changing this entry, right? Because I know that axis2 by default has 1 here, 1 here and 0 here. And what I have said is, okay, I have saved the predictor matrix from the setup run in this object pred, and I'm saying that the third row, second column should be a 0 and not a 1. And then when I run my mice, when I call mice here in the predictor matrix argument, I give this spread. And then if I run this, I see that this is my new predictor matrix. I'm not saying that this is the way to go in this case. I'm just illustrating in case we do not want one of the variables to be used to impute some other variable by some reason, that there is a way we can fix it. And in this case, it's not a bad idea, because the way I have constructed is that y was constructed from axis 1 and axis 2 and some normal noise. And by construction, axis 1 and axis 2, they were generated, sorry, independently, so their correlation is very low. If I do correlation, say, of axis 1 and axis 2, why is it giving me a 0? Well, if we run our data, possibly I haven't run the data, but the correlation is very low. By construction, they were generated in an independent way, whereas obviously axis2 and y, they are correlated because y was constructed using axis2. So it's not a bad idea that we say, okay, I do not want axis1 to impute axis2. It's not hurting here, I think, but in case we have many variables, so we need to pay attention to this. But this is just illustrating how doing a setup run of mice, and we can change the method that we are using to impute the variables, and also the predictor matrix that determines which variable variables contribute to the imputation of the variables with missing values. And now I can proceed to, I have explored step 1, the usage of the function mice. Now I can proceed to do my analysis of interest. And imagine that my analysis of interest is just to use the model that I've used to generate data. So I just come here and use the function with. I pass my imputation object. This is the first object that I have created using the setup of, not the setup, using the defaults of mice. So 5 donors, 5 iterations, and I fix the seed to be 1, okay? And I pass this object to the function with, and I'm saying what is the analysis that I want to conduct. And in this case, I want a linear regression model of y on x is 1 and x is 2. And if we run this, okay, I have already saved the results of my 5 linear regression models in this object fits, and the class is mi RA, which stands for multiple imputed repeated analysis, just the name of the class of the object. And then I can see that what I have done is I have conducted 5 linear regression models, one regression model for each of the completed data sets. And for instance, I can extract the results from the first model, and it's going well. We know that the true beta 0, beta 1, and beta 2 were 5, 3, and 1. And here are the results for the second imputed data set. So this is exactly the output from a linear regression model, because that's what we are doing to each of the completed data sets. Okay. And now finally I can pull my estimates together, my regression coefficients, and we know how to do that using Rubin rules. So here, that's what I'm doing. It's the function pull, and I'm passing as argument fits. Okay. And if I do this, it did not produce the the HTML with this, but I will uncomment. And that's it. Now the class of the object is MIPO, which stands for multiple imputed pooled outcomes. And I have several um, the output includes several things. Here, the estimate is the pooled regression coefficient estimate. So the regression coefficient for beta 0, beta 1, and beta 2 pooled across the 5 imputed data sets. And we know that this is just the average of beta 0 across all data sets, the same for beta 1 and the same for beta 2. Here, U bar, it's giving me the within imputation variance. B is the between imputation variance. T is the T statistic, the usual T statistic, the pooled one for the linear regression model. Here it's some degrees of freedom for the complete data set. We can ignore these. Also the degrees of freedom. We do not need to use these ones because then mice computes the rest of the quantities based on these degrees of freedom for us, the p-values, for instance, and the quantiles of the confidence intervals. And then we have these 3 columns, and this is the relative increase in variance due to the missing values. And we have seen this in the last week video. So this is basically the relative increase in variance that we have due to missing values. And we know that this is B plus B over M over the within imputation variance. So it's this expression here. And here, lambda, it's the proportion of variance in our parameter of interest, in this case, beta 0, beta 1, and beta 2, due to the fact that we have missing values, and is similar to the relative increase in variance, but rather than dividing by the within imputation, we are dividing by the total variance. And we have also what the total variance is in the slides of the last lecture, is B plus M plus U bar. It's basically the between imputation plus the between imputation divided by the number of copies of the dataset that we are using plus the within imputation variance. And this FMI is the fraction of missing information. It was defined by Rubin. It's related to the relative increase in variance, and I will not give the details. We will not be using this. Okay, so we have a lot of things. Then I've asked for the summary because it depends on the analysis that we are doing, what I want to, what is the output that I want. Here I said, okay, let's look also at the summary. And the summary here I have here the summary. The summary gives me the p-value and also the p-value. Of course, I know that because I have the way I have constructed, I know that x is 1 and x is 2 are significant. And here the 2.5 and 97.5 are the lower and upper bounds for the confidence interval for my pooled estimate. We also have how we have compute in the last week's slides how to compute these lower and upper bounds, but mice does the dirty work for us, let's say. And also I can say, for instance, if I'm not interested in all the columns, imagine that I'm only interested in the estimate, the standard errors, and the the bounds of the confidence interval. I can just select this column, so I don't need to look at everything. So what we select here depends on the analysis that we are interested. I think it's good to look at the beginning at everything, but then we can work with a more restricted summary subset, say. And also the mice package, in case we want to compute the R square from our pooled analysis, we know what is the R square for each of the individual analysis. We can extract that from our second step, but then how to pull it, we need to do something else, but mice does this for us. So if I use this command pool r squared, and if I say adjusted equal to true, so to have the adjusted r square, we know that the r squared, the more variables that we include, it will increase, and the adjusted r square adjusts or penalize for the number of variables that we are including. So not necessarily it increases as we include more variables. And the main message is that I pass the object from my second step and I can get an adjusted R square. Of course, in this case, is very high because I know how I have constructed my data. But for real analysis, this is an interesting quantity. And also, now just to conclude this part, let's see what is the effect of m. So what we have used m equal to 5. So now I will change the seed. Okay, I will keep m equal to 5 and I will change my seed. I have used seed equal to 11 and to 111, and the initial one was 1. And here, let's see, my estimates, there will always be some Monte Carlo, some difference. They will not be exactly equal, but I do not want them to change very much if I change the seed. And nothing too wrong is going on here for the standard error of beta 1.11, 0.08. So there is some variation. It depends on us or on the specific analysis what we are willing to accept. The p-values are not changing, of course, because they were very low here. So and the bounds here, I see that for some here I have 4.35, 4.27. So there is some variation. Let me increase, use the same seeds, but then use 20 imputed data sets. And we know that how many imputation depends on many things, and also on the proportion of missing values. Here it's relatively low. It's kind of, it's 13% of our data set. And we see that by m equal to 20, we already get more stable estimates. And of course, as we increase m, I've tried 50 and 100. Basically, the differences are then very, very small. And basically, it says that one can be more confident in one specific run. And we were not lucky because of our seed. In this case, m equal to 20 was already fine. I haven't tried m equal to 10, but maybe m equal to 10, the major differences disappeared. So you can try. And that's basically it for this week. So it's mice for univariate missingness, and we will finish next week with mice for multivariate missingness and some scenarios where mice might fail. Okay, thank you and see you next